Hello and welcome. Today I'm going to be talking about my paper, Meta Learning, a Solution to the Hanabi Ad-Hoc Challenge. Over the course of this talk, I will first explain the game Hanabi, and then I'm going to talk about the Hanabi Open Agent Dataset, um, which is a group of agents that anybody can download and use to study Hanabi. I'm going to then convince you of why Hanabi is worth studying, why you should be excited about it. Um, I'm going to introduce the Hanabi Ad-Hoc Challenge. And then I'm going to introduce a meta-learning solution that we explored and the results that we got. Okay, let's get started. Okay, so Hanabi, what is it? So it is a cooperative game for 2 to 5 players. We're only considering 2 players for this work. Um, it is most similar to a sort of cooperative solitaire. The main gimmick, if you will, is that the players cannot see their own cards, only the cards of their teammates, but they have to play their own cards. So in order to correctly play a card, so we have these 5 towers here in the center, and we want to, so here we see we have these 5 towers in the center, and we want to create ascending um, towers we want to create 5 of them to win, or to score the most possible points. Um, the players have to play the correct cards from their hands without knowing, without seeing the cards. Okay, so how can they know any information about them? Well, one of the possible actions that you can take during your turn is to use a hint token. So those are these guys right here. Notice how there's only 8 of them. Using a hint token, we can tell partner about either all instances of one color. So I could point out all the red cards, for example, in their hand. Or I could point out all instances of a number, so like all the ones, for example, I could point them out. So this way we can give color or value hints during our turn. Now, that's not the only kind of action we can take, as you'll notice, right? There's only 8 hints. Those go pretty quick. We got to get them back somehow. Well, we can do that by discarding cards. That's one of the other actions that we can take during our turn. But we must be careful. If we discard both 2s here, then we will no longer be able to complete the red tower, and we'll be forfeiting points. Finally, the last action you can take on your turn is to actually play a card. So you can take one of 3 possible actions: hint, discard, or play a card. If you play a card that cannot be currently played, you will lose a life token. There are only 3 of those. If you lose all 3 life tokens, you get 0 points. As a matter of note, the total score at the end of the game is simply counted as the number of cards you managed to put down. In this case, you see a perfect game of 25 points. All right. So let's talk about conventions. Um, as you saw earlier, there's a hint economy. Um, there's a fine balance between giving hints and between discarding cards. And since you don't know what cards are in your hands, it's very important to properly communicate to your partner. Partner is if you're playing more than 2 player, to your partner, um, what cards they have in their hand. But the game is set up as such that you cannot just tell them, okay, well, this is all your 2s, and then later tell them this is all your blues, and then have them only play cards they're perfectly certain about. There are, of course, bots like that, but they achieve fairly low scores, I think in the sub-10s. Um, you'll see later that the agents in on the open agent data set achieve more in the mid-10s. Um, Okay, so if we can't tell our partners full information about the cards in their hand, what could we do instead? Well, we could have conventions. So let me give an example convention that helps to save on hints. So a very popular convention that Hanabi players use is that they will put the cards in their hands in order of least to most recent. So let's say that this girl had just drawn this red one, then she would put this card here in the rightmost position. Um, this girl would know that this card was in the rightmost position, and the convention, maybe that they had agreed on in the beginning, is that if this girl receives any type of hint, either color or value, about her most recently drawn card, then she would know that that is a playable card. So the advantage of that, of course, is that she only needs one piece of information in order to play that card. Hints, conventions such as these make the game possible and make it even reasonable to score full 25 points. But a problem is posed. How can you play with an unfamiliar group? So, of course, you would want to build some sort of a mental model of your teammates, and then you would want to use that mental model to search over possible future states and pick an action which maximizes expected future reward. Right as a side note, this workflow pops up in many other domains. This is a pretty standard way of approaching problems where we don't know the individual that we are cooperating with or that we are competing against. So this kind of workflow is pretty general beyond just the domain of Hanabi. In this case, though, for Hanabi specifically, we can actually just focus on building a mental model. And that is because mirroring the partner strategy is typically a good enough approach and will net us a good amount of points. It is perhaps possible to use this mental model. I mean, it is definitely possible to use this mental model to search over possible future states and pick the action which maximizes. But this is not something that we focused on for this paper. It's something that would be interesting to explore in future work. But yeah, so we're really just focusing on this first bullet point. So okay, let's formalize this ad hoc scenario a little bit. So you just observed a group of Hanabi players that you've never seen before play 10 games, and now you must stand in for one of the players, and the team must play well. This is the essence of the Hanabi ad hoc challenge. Okay, well, so we're gonna have to build a mental model of an unfamiliar player. Now, for this work, we decided we wanted to explore meta-learning approaches. Specifically, we settled on using a model-agnostic meta-learning, which we'll explain later. It's a pretty popular form of neural meta-learning. However, we are going to need a group of Hanabi players to do this because for meta-learning, what's important is to have a group of high-quality yet diverse agents that can play the game. This is because if they were not high quality, then of course we could not learn high quality. And if they were not diverse, if they were all more or less using the same strategy, then we could not expect to learn a wide breadth of strategies from which to generalize. Okay, so what are we looking at here? These are all of the agents in the Hanabi Open Agent dataset currently. The dataset so HODE is easily extensible, and there are plans to add more in the future. So these agents here, we can see that on the on diagonals. So on the diagonal of this this table, we can see that when, for example, SimpleBot plays with SimpleBot, you get a high score. So 60.8, 18, these are decent scores, roughly corresponding to intermediate play by humans. On the off diagonals, we can see that we're getting some fairly low scores, a lot of zeros, a lot of low single digit numbers. That is indicative of the particular pairing striking out a lot. So that means that they're giving each other hints that they do not understand, they do not share the conventions, and so they strike out with great frequency. So this sort of showed us that HODE is an appropriate data set on which to train a meta-learning model. So let's talk about them a little bit. Okay, so we take HODE, we do this lengthy training via MAML. This creates a generalist player. Think of the generalist player as something that's just basically been trained on a lot of different players, and specifically can be, with a single gradient update, modified to be a good replica of an unfamiliar agent. So this is sort of the essence of MAML, that we train on a lot of agents in such a way so that when we take 10 games from an unfamiliar agent, with a single gradient update, we can get a good replica of that unfamiliar agent. And so this was, again, going back, this was how we are building a mental model of the unfamiliar group. Okay, so let's go ahead and take a summary of the experimental methods before we go on to the results, just to have a little quick summary. So we took agents from various online code bases. We created neural network imitators of them, thereby porting them to Python. So they can play with each other, and we can validate the data set as a good option for meta-learning. Then to actually employ meta-learning, we trained MAML on HODE for 5 bucks. We got the gradient update for the held out agent. And then we're going to do a couple of comparisons to show that we have achieved reasonable results here. Okay. So let's start out with the baselines and emphasis on base. So we test each of the bots against a random partner. So on average, we get about 4.3 points, which is not great. Even worse, though, is when we test the agents against a naive MLP. What is this naive MLP? Well, what it is we just take those 10 games from the held out agent. So if SimpleBot is held out, right, we take 10 SimpleBot games, we train a neural network on those 10 games, and then we play the resulting network with SimpleBot to get the score. So we can see that 10 games is not enough to learn Hanabi from. On the contrary, when you have MAML, which learns from the other bots, it is able to transfer its knowledge from the other bots to the unfamiliar bot. We can see that here, and so zero shot, low shot. So zero shot means that we do not do the single gradient update that we talked about. Low shot means we do it. So we can see that just the generalist neural network is on some occasions, even better than the random partner, but so on average is better than a random partner. And when we do that gradient update, we see that we get an improvement. However, we did notice an interesting effect. So this improvement from the single gradient update actually disappears once MAML is trained for enough epochs. So here, this is a little bit less than halfway through training. We notice that this effect is still here, but later in the training, we notice that it disappears. And so this has actually been documented in a few other domains. So, we can here say now with some more certainty that this effect is inherent to the MAML algorithm. Yeah, with that, we're more or less done here. So please let me know if you have any questions. I'd be more than happy to answer them. Thank you very much.